Welcome to this explainer. Have you ever actually stopped to think about the sheer magic happening inside your computer when you boot up a modern, hyper-realistic video game? We totally take it for granted, right? But under the hood of your graphics card, there's an engine performing absolute feats of computational impossibility every single second. Today, we're going to unpack exactly how that magic works by exploring the microscopic architecture of the GPU. So, here's our roadmap for today. First, we've got the gaming calculation problem. Second, transistors and GPU layout. Third, rendering games with SIMD. Fourth, the SIMD versus SIMT shift. And finally, number 5, solving warp divergence.
Okay, section 1, the gaming calculation problem.
To truly appreciate the hardware, we first need to wrap our heads around this central, literally impossible problem we're exploring today. The sheer unimaginable scale of modern video game rendering. 36 trillion. If you want to run a deeply realistic game, think something like Cyberpunk 2077, your graphics card needs to crank out roughly 36 trillion calculations every single second. To put that into perspective, imagine doing a long multiplication problem once every second. To match the power of a modern GPU, you'd need every single person on Earth doing one calculation per second, and then you'd need to multiply our entire planetary population by about 4,400 seriously. That's 4,400 Earths filled with people, all working together, just to match what this tiny little piece of silicon does in 1 second.
And this brilliantly illustrates why we can't just rely on our standard computer processors for this. You see, your computer's CPU, the central processing unit, is basically a jumbo jet airplane. It's incredibly fast and very flexible. It can land at thousands of airports, carrying diverse payloads. It is built for complex, varied tasks. But a GPU, a graphics processing unit, is a massive cargo ship. It's definitely not as fast or flexible as the jet, and it only travels between specific ports. But man, it carries a staggering amount of bulk cargo. When rendering graphics, we don't need complex, highly varied logic. We need simple, repetitive calculations blasted across mountains of data all at once.
Moving on to section 2, transistors and GPU layout. So how do you physically build a bulk processing cargo ship out of silicon? The answer lies in nested complexity. If we open up a modern graphics card, we find a central chip, like the GA102, built from an astounding 28.3 billion transistors, and they're organized in a super strict hierarchy. It's like a giant puzzle. The chip is divided into 7 graphics processing clusters. Inside those are 12 streaming multiprocessors. Inside those are 4 warps, and inside each warp are 32 CUDA cores. Each one of those individual CUDA cores packs about 410,000 transistors. We literally just zoomed all the way in from a massive 28 billion transistor city, down to a single neighborhood, down to a single core, illustrating exactly how the physical layout supports these massive parallel operations.
Now, the absolutely crucial point here is understanding what that single CUDA core actually does. It sounds incredibly complex, but at its heart, it's just a very simple calculator. In fact, a dedicated section of about 50,000 transistors inside that core exists just to perform one basic operation: fused multiply and add, or FMA for short. It simply takes number A, multiplies it by B, and adds C. That is literally it. It just does this basic arithmetic over and over again, unbelievably quickly.
Which brings us to section 3, rendering games with SIMD. Okay, now that we have our cargo ship built out of thousands of simple calculators, how is it directed by software to actually render the graphics on your screen? To answer that, we have to introduce a fantastic technical term: embarrassingly parallel. I know, it sounds like a joke, but it's a very real classification in computer science. It describes a problem that requires almost zero effort to divide into separate, independent tasks. Rendering a 3D environment perfectly fits this description because calculating the position of one object in a video game usually has absolutely no dependency on calculating the position of another object across the map. Let's look at a tangible example of this in action. Imagine a 3D cowboy hat sitting on a table in a game. That hat alone is built from around 14,000 specific points, or vertices. Initially, those points are measured relative to the center of the hat, what we call model space. But to render the whole room, the game needs to know where those points are in the larger world space of the game environment. To figure this out, the GPU takes the exact same addition instruction and applies it to all 14,000 vertices simultaneously, instantly shifting the entire hat into the shared world space.
And that brings us to the core operating principle of GPUs, SIMD, or Single Instruction Multiple Data. The GPU doesn't process those 14,000 cowboy hat vertices one by one, no way. It takes that single mathematical addition instruction and blasts it across all the separate data points at the exact same time, utilizing those thousands of simple CUDA core calculators we talked about earlier in parallel.
Now for Section 4, the SIMD versus SIMT shift.
This SIMD architecture was the gold standard for a really long time. But as games got more complex, we needed to push performance even further, which led to a major evolutionary shift in architecture around 2016. Think of the original SIMD architecture like a rigid phalanx of soldiers. Every thread in the warp followed the exact same instruction at the exact same time, marching in perfect lockstep using a single shared program counter. But newer GPUs shifted to SIMT, single instruction, multiple threads. While they still receive the same core instructions, the threads are no longer forced to march in lockstep. Each individual thread is given its own program counter, allowing it to progress at its own rate while utilizing a shared L1 memory cache to exchange data.
Finally, Section 5, solving warp divergence.
So why did GPUs actually need to make this shift to SIMT? Well, we have to talk about a massive architectural bottleneck that SIMT was explicitly designed to solve. That bottleneck is called warp divergence. Remember those rigid lockstep soldiers of the old SIMD architecture? What happens when they encounter a fork in the road in the code? An if-then statement, where some data requires one calculation and other data requires a completely different one. Well, in the old system, the whole phalanx had to stumble. The threads taking path A would execute, while the threads taking path B sat completely idle, literally wasting precious computational time until they could sync back up.
Modern SIMTIC architecture beautifully conquers this bottleneck. By granting those individual program counters we just talked about, threads can now seamlessly manage conditional branches independently. If thread A needs to take a different path than thread B, it just does it. They evaluate their distinct instructions and then flawlessly reconverge later on. This flexibility is what dramatically improves efficiency and, honestly, saves the performance of modern GPU architectures when dealing with highly complex game code.
So we've journeyed all the way from trillions of calculations down to the single transistor and seen how parallel architecture renders the digital worlds we love to play in. But I want to leave you with a provocative thought to ponder. If these exact same massively parallel principles, blasting simple math instructions across millions of data points simultaneously, are so perfect for pushing pixels in a video game, how might this exact same architecture be the fundamental engine fueling the quadrillions of matrix calculations required for modern generative AI? The hardware that renders your favorite games is the very same hardware simulating the neural networks of the future. Something to think about.